And is on polynomial functions of higher degrees. So we're going to be spending the rest of the chapter talking about polynomials. So we're going to be doing things from Algebra 2, like the P over Q, right, rational roots theorem. We're going to be talking about end behavior. We're going to talk about how to graph polynomials. So we're doing a lot with this. Long division, do you guys remember long division, synthetic division? Yeah, we're doing all of that throughout this chapter. So we're going to start with the basics today. So a polynomial is by definition something that's like x to the n, right? So n is some kind of positive degree. And the degree of the polynomial is the largest degree of the individual pieces. Do you remember that? Neil, can you put your computer away? So it says, write the polynomials in descending form and find the degree of the following polynomials. So descending form we sometimes call standard form. So if we're writing it in standard form, we're just going to write it so we start out with our highest exponent. So we'd have 8x to the 9th. We don't have an 8, like an x to the 8th, but we do have a 7. So minus 6x to the 7. No 6, but we do have a 5, so plus 7x to the 5th. No 4, no 3. We do have a 2, so minus 10x squared. And then plus 9. Okay, so do you guys all remember standard form, what that means? Really, I think standard form was just invented to make it easier on math teachers to grade your papers, because if you write it in one standard way, we can quickly grade it. So, all right, so if I'm finding the degree, our degree is going to be that largest exponent. So in this case, our degree would be a 9. So our degree tells us a lot about our polynomial. So do you guys remember this part? Does it look like this on the ends? Does it look like this on the ends? Does it look like this on the ends? Or does it look like this on the ends? So 1, 2, 3, or 4?
2.
It looks like 2. It's going to look like an x cubed, right? It's odd and it's positive, so it's going to look like positive x cubed on the ends. Okay, so we're going to talk about that in just a second. So the next one is going to be 10x to the 10th. Nope, that's not our highest, is it? 4x to the 13th plus 10x to the 10th minus 3x squared plus 8x plus 6. That would be our standard form. So our degree then would be 13. So again, it's an odd degree, so it's going to do what Maury calls the John Travolta, right, where one goes up, one goes down, like that. Did he call it that last year? No, he didn't? I'm surprised. You guys are just getting... You're too young these days. You don't know who John Travolta is.
Jimmy's. Yeah, that's true.
They call it sprinkles, like on ice cream, Jimmy's.
Jimmy's? Oh, that must be a weird Boston thing. He's weird. All right, so end behavior. So that's what we're saying here. So if it has an odd degree and the leading coefficient is positive, it's going to look like x cubed. So x cubed on its ends looks like this. So we could be doing lots of things in the middle. It could go up and down, up and down, up and down. It could do lots of things, right? But we know that in the ends, it's going to be like this, okay? So if the leading coefficient is negative, but it's odd, it's going to be the other direction, which is what I was saying was what Maury usually calls the John Travolta. Both of those are, you know, putting your fingers up in the air. Up and one's down. Even degree, that's going to be like x squared. Oops, so it's going to be where both of them go up. And then negative is where they're going to both go down. Okay, so if you remember in Algebra 2, we wrote this a certain way. So we would say, as x goes to infinity, don't write this, I'll tell you another way to write it. So as x goes to infinity, y also goes to infinity. Okay, and what that meant is as x got really big to the right, so as I went to the right, my graph went up. Does that make sense? So y got positive. And so this one we had written as x goes to negative infinity, y goes to, it goes down on that side, so negative infinity. Does that make sense? You guys remember those? We're going to write this differently in pre-calc because it's leading, this is why it's called pre-calc, it's leading to calculus, okay? So in calculus we use something called limits. So the way we're going to write this is we're going to say the limit, and then below limit we're going to write real tiny. So we're going to say x goes to infinity. So the limit as x goes to infinity of our function is equal to infinity. So limits are the y value you're getting closer and closer to as x goes in a certain location. So what we're saying here is as x gets bigger, as x goes to infinity, where does y go? Y goes up. It goes to infinity. So it's exactly what we did in Algebra 2. We're just writing it differently. So on the left-hand side, I'm going to say the limit as x goes to negative infinity of my function is negative infinity. On the second one, I'm going to say the limit as x goes to positive infinity of my function. Where does the y value go? It goes down, right? On the right side, I go down, so negative infinity. And the limit as x goes to negative infinity, so as I go to the left, my function goes up to infinity. Does this make sense? Do you guys get it? It's just a different way of writing it, so don't let the limit scare you. All right, on the other ones, we're going to say the limit as x goes to positive infinity, so as I go to the right for my graph, what happens to my y value? It goes up. It goes to infinity, yeah. The limit as x goes to negative infinity of my function also equals infinity. It goes up as well. Does this all make sense? The limit as x goes to infinity of my function would be negative infinity. It goes down. And same thing for this one. So the limit as x goes to negative infinity of my function is also negative infinity. You get used to writing limit, 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 limit in calculus. I used to let my students write L squiggle for limit. And then I had a student by the name of Leonidas Georgicolopoulos, was his name, Lee, who did that on his AP exam. And then I stopped letting people write it as L squiggle because he was like, oh, I didn't know I couldn't do that. I was like, I was just letting you shortcut for my class, not for the exam. All right, anyway, so number one. So identify the leading coefficient, degree, and end behavior. So our leading coefficient is the number all the way out front. It decides whether we have a positive or a negative. So if it's positive x cubed, negative x cubed, positive x squared, negative x squared. So one of those four possibilities. So our leading coefficient in this case is -1. Our degree is 4. Our end behavior, since it's negative and it's x to the 4th, it's going to look like this on the ends, right? So that's our end behavior sketch. So if your book was asking you to write limits, you would say the limit as x goes to infinity of f of x is negative infinity, and the limit as x goes to negative infinity of f of x is also negative infinity. So again, we're saying as I go to the right, this is what x goes to infinity means, I go down. As I go to the left, I go down. That's how that's read. All right, our leading coefficient on the next one is 2. Our degree is 5. Our end behavior sketch is it's positive and odd. So show me with your hands what it does. Yeah, good. So it's going to look like this on the ends. So we're going to say the limit as x goes to infinity of our function is equal to what? Infinity. And the limit as x goes to negative infinity is negative infinity. Perfect. Good? All right, so to identify whether it's even or odd and positive or negative. So do they go in the same direction on the ends? No. So this one's odd. And is it positive or negative? Does it look like positive x cubed or does it look like negative x cubed? Yeah, it's negative. So odd and negative. So how about the next one? Even and negative. Perfect. Do you wish the whole test was like those questions? Those are my favorite. Easy. All right, so if you remember, books can ask lots of different things. We can phrase the same question in several different ways. So if I say something like, find a root of the function, or find a 0, or find the x-intercept of the function, or find a solution to the polynomial equation where you have a polynomial equals 0, or find a factor of the polynomial, all of these things mean the same thing. Okay, so x-intercepts, roots, zeros, those are all the same thing. So general rules for factoring. So we always pull out the greatest common factor first. If there are 4 terms, we do factor by grouping. If there's 3 terms, we do our 2 sets of parentheses. And we also look to see if there's 2 terms. In that case, it would be the sum or difference of 2 cubes or 2 squares. We can't do the sum of 2 squares, though. And our trinomial thing is the reverse factoring. So we're going to practice factoring over the next couple days. So the first one says find the zeros of the function. So do we have a GCF, first of all?
Yes.
No, we don't. We don't have anything we can pull out because we have that 1 x cubed, right? So this is 4 terms, so we do our factor by grouping. So we're going to split it down the middle, and we're going to ignore the left side, or the right side of the equation right now. So only looking at the left side, if I have x cubed minus 6x squared, yes, there is a GCF. So I'm going to pull out the GCF from just this part. So I have an x squared I can pull out. When I do, I have x minus 6. On the other side, I want to have an x minus 6. Is there something I can pull out? Yeah, I can pull out a 2. And I always pull out a number and a sign, so I'm going to pull out plus 2. Okay, so if I had this, you guys would totally know what to do on the next step. Like if I had x squared y plus 2y, you'd be like, oh, there's a GCF. The GCF is y, right? And then you would pull that y to the front, and you'd be left with what was not the y, the x squared plus 2. That's what we're doing on the next step. It just doesn't look like that. Do you guys see how we have a GCF again? X minus 6 is now a GCF. So we pull the entire x minus 6 to the front, and we're left with x squared plus 2. Okay, and you can FOIL that out. You would see you get the same thing. Is this me beeping or you? So we end up getting this. We then set it equal to 0 to find the zeros, or x-intercepts, right? X-intercepts set the y equal to 0, and we set each piece equal to 0. So I'm going to have x minus 6 equals 0, and I have x squared plus 2 equals 0. So the first one, I get x equals 6. The second one, I don't get a real solution. But we are going to talk about imaginary solutions, or complex numbers, right, later in the chapter. So let's go and find it. So I subtract the 2 over, so I get negative 2. I take the square root and write plus or minus. This is all coming back to you. We get plus or minus I root 2 would be that answer. Now I think on your homework, it's not going to ask you for complex solutions yet, so don't worry about that on your homework. But we're going to talk about complex numbers. We'll review that as well. All right, so the next one, yes, we do have a GCF on this one. So I would probably pull it out before you even start. All right, so if I have a 3 in common, I pull that out, so I get 4x cubed plus x squared minus, not 6, 8x minus 2. And then I can just factor by grouping on that part that's inside. So if you forgot to pull out the GCF, it will work out fine. You'll just kind of continue factoring and pull out a GCF later. So I'm going to have an x squared. When I pull out the x squared, I have 4x plus 1. You need that plus 1. A lot of people forget that. So if I want a 4x plus 1 over here, and I have negative 8x minus 2, what am I pulling out? Yeah, negative 2. Perfect. So when I do this, I have 4x plus 1 pulled to the front, and I have an x squared minus 2. But I also have that 3, so I'm just going to pull the 3 out. And I'm finding the zeros, so I'm setting it all equal to 0. So the first one, I don't have 3 equals 0. That doesn't work. Do you guys see if I had 3 equals 0, that's not giving a solution? So I say 4x plus 1 equals 0, and x squared minus 2 equals 0. So when I subtract the 1 and divide by 4, I get negative 1/4. What do I get for the other one? Plus or minus the square root of 2. Perfect. So I have 3 solutions. Since it's x cubed, you guys remember the maximum number of answers you can have is 3. All right, so that's starting that next section for you, so we'll finish this up next time, but you guys can go on and start that homework as well. Okay, roots and zeros, x-intercepts, those are all the same thing, right? So in your examples, we had done the first 2. So the first one was factor by grouping. I guess the second one was factor by grouping as well. So let's try some of these ones that involve our 2 sets of parentheses, right? So factoring using trinomials, difference of 2 squares, and so on. So number 3 says that we have f of x is equal to 9x squared minus 16. So our instructions said find the roots, or find the zeros, aka x-intercepts. So we're going to set our f of x equal to 0, and we're going to factor. So this is a special type of factoring problem. It's called the difference of 2 squares. So basically it's like we had 9x squared plus 0x minus 16. So we want our outer and inner swoops to combine to be 0, basically. All right, so in order to do that, we need exactly the same thing in the parentheses, except our signs are going to be different. So we're going to have 3x plus 4 And we're going to have 3x minus 4. Okay, that will give us our 9x squared when we multiply our first terms, our negative 16 when we multiply the last terms, and you guys see how our outer and inner swoops combine to be 0x. So when we set each piece equal to 0, we get two solutions. So the first one is negative 4 over 3, and the second one is positive 4 over 3. So the next one, we're going to set our f of x equal to 0. We're going to factor. So we have our x and x. We want to multiply to be 8. So let's try like 4 and 2. And we want our outer and inner swoops to combine to be negative 6. So if they're going to combine to be negative 6, we need a negative and a negative. So when we set each one equal to 0, we get x equals 4 and x equals 2. Can most of you guys go straight to the point where you're saying, oh, x is 4, x is 2, without writing x minus 4 equals 0 and solving it out? All right, so the next one, so we're factoring. And this is where you guys start to be better at factoring, and you're starting to see where you're putting the 2 and the 1. Okay, so we have our 2x and our 1x. We know we need our last terms to multiply to be 2. So think about where I'm putting the 2 and where I'm putting the 1. Do you see the outer and inner swoops happening? So if I put the 2 on the far right, I would have a 4x. And if I put the 1 in the middle, I get a 1x. Can 4x and 1x combine to be that negative 5x? Yeah, so if I have a negative and a negative. So I get x equals, can we do this one in our head? What do we get when we have 2x minus 1 equals 0? 1/2. Can you guys all do that? If you can't, just go ahead and write it out. And what we're doing is we're adding the 1 to the right side, and then we're dividing by 2. So we get 1/2. And then the other one is x equals 2. All right, so this next one I put on here for a reason, because a lot of people just kind of panic when they see ones like this. They're like, wait, I don't know how to factor this. You do, right? It's just a GCF. We're pulling the GCF out. Now, personally, I don't like to have a negative out front, so I would pull a negative all the way to the front outside of parentheses. So I'm going to have a negative x, and then I would need a positive x squared minus 4. So you can check by multiplying the negative x in. See how we have negative x cubed and then plus 4x. That's what we wanted. So we set it equal to 0. And we can continue to factor on this one. X squared minus 4 is the difference of two squares. So we have x plus 2 and x minus 2. So we definitely get the answer of x equals negative 2 and x equals 2. But you guys all see that there's one more solution. Yeah, so if we set that negative x equal to 0, we get x is equal to 0, exactly. So we have 3 solutions. So that kind of brings us to like the fundamental theorem of algebra, which we talked about in algebra 2. So if I have something that's x cubed originally, x to the third, I'm going to have 3 solutions. Now they could all be the same solution. So if I had something like x minus 10 cubed, and I asked you to find when it was equal to 0, that would be the solution 10, but it would be 3 different times, right? Because it's x minus 10 times x minus 10 times x minus 10. Does that make sense? That's called multiplicity. Do you guys remember what multiplicity does to a graph? Yeah, we're doing this throughout the chapter. So multiplicity on a graph means if 10 was our solution, so if we're out here at 10, and it was our answer 3 different times, it's going to look like a little tiny x cubed graph on that 10. So it's going to do like a little tiny swoop like that, okay? And then it would continue on. Does that make sense? But if we had other things like x minus 2 squared, that means at 2, I would have to bounce on 2. I'd have to look like a little parabola there. So it would look like something like that. So we have our x cubed, but we also have a parabola shape on that one. Does that make sense? Okay, so these are things that we'll continue to talk about throughout this chapter, so don't worry if you don't get it right now. Okay, so write a polynomial function that has zeros of -1, 0, and 3. So on your last homework, a lot of you guys didn't know how to do this yet, because I hadn't talked about it yet. But if we have a 0 of -1, that means that we had to have x plus 1 as part of the factorization. Because remember, if I was like setting it equal to 0, right, x equals -1 would be an answer. So we're going to start with our x plus 1. What if x equals 0 is a 0?
So you just add in another x after.
Yeah, it's like you just have an x. You can put it out front if you don't like it in the middle. You could put it like right there. It's like x minus 0. And then 3, so we have x minus 3 on the right. So we're trying to write a function in the end, so let's write f of x, or you could do y if you want. And we want to multiply this out. So we're going to go ahead and distribute it, or distribute. So we're going to FOIL it, sorry, I'm using the wrong words. So I'm going to FOIL this part out. When I do, I get x times x is x squared. My outer is negative 3x, my inner is plus 1x, and my last is negative 3. So I get x squared minus 2x minus 3. But I don't forget about that x as well that I had out front. So our final solution is going to be x cubed minus 2x squared minus 3x. Okay, now notice this says there are many solutions. It's like, wait, I just got one. Are there more than that? There could be. There's an infinite number of solutions. And what that has to do with is the number that's out front. So I just have like a 1x. I could have had 2x, 8x, negative 7x. I could have had lots of different things out there. Does that make sense? I know it's distracting when another class is coming up to the window. Very distracting. Just hanging out right there. I'll have to close the blinds. All right, so does this make sense? I could have some kind of coefficient out front. So if I had zeros of 2, negative 4, and 5, I would set it up with x minus 2, x plus 4, and x minus 5. But I can put any number out front. I could make it negative, which will flip it upside down, right? So I could have lots of different answers. Does that make sense? So I think on your homework it said, find two functions, one positive and one negative. That would have those zeros. Maybe this is the upcoming homework. All right, so intermediate value theorems. This is the last one. This is a very important theorem, not necessarily in pre-calc, but we use it a lot in AP Calc. So it says, let a and b be real numbers such that a is smaller than b. So we're going to put a little number line, and a and b are on there. And f of a is not equal to f of b, so they're not at the same heights. So we'll call that f of a and f of b for their heights. Then in the interval a to b, f takes on every value between f of a and f of b. So the way we typically phrase this in calculus is we say, there exists a number n between f of a and f of b. So let's say I have any height here in between. And I'm going to have this little dotted line across. So let's say this is at a height of n. I have to go through that line. I have to have a y value that has that height because I use the word, well, I use the word polynomial, but it's a continuous function. Okay, so we have a continuous function. So think about polynomials. You guys all know what polynomials are. Like when I graph them, this would be like an x cubed one, x squared, right? X to the fourths can sometimes look like w's if we have like a minus x squared. Polynomials are what we call smooth and continuous. Are you ever doing like something like this for a polynomial? Jumping from one value to another? No. Okay. So we have a continuous function. So we have to go through somewhere this line. At least once. It could go through more than once, but somewhere. So it has to go through at some value between there. Okay, that's the intermediate value theorem. All right, so it's often used when we're finding zeros of functions. So the first one says, for f of x equals x cubed minus x squared plus 1. So we have a polynomial function. Show that there's a 0, so an x-intercept, between negative 2 and 1. So what we do is we just find those heights at negative 2 and 1. So we're like, oh, at negative 2, I get negative 8 minus a 4 plus 1, I get negative 11. And at 1, I get 1 minus 1 plus 1, so I get 1. So I was always a very visual math student. I always had to like think of the picture. So if you have to think of the picture, here's what's going on. At negative 2, we're at a height of negative 11. Whoops, I didn't plan this very well. And at 1, I'm at a height of 1. And we have some kind of polynomial function. So we have some kind of curve that's going through here. So where do I have to cross I have to cross somewhere between -2 and 0. Okay, so I could have some kind of polynomial connecting these, but I have to cross somewhere between, I didn't really pass my vertical line test there, did I? Somewhere between here and here is where I have to cross. Mine looks like it's crossing at 0. I don't know where it's crossing. Okay, does that make sense? So then it says, try to estimate an interval that's half a unit long. So right now, we're between what two numbers? -2 and 1. So let's say we try to like squeeze it in a little bit to estimate an interval that's half a unit long. So what if I tried like -1? F of -1 is -1 minus 1 minus, or plus 1. So I get 1. So now I'm between, so at -2 I was at a height of -11. I'll put it down here. And at -1 I was at a height of 1. Did I mess something up?
Yeah,
Here I'm
it
1.
should be -1. Yeah, that'll be -2 plus 1. I'll be -1.
Oh, -1, thank you. Okay, yeah, 1. So then here I'm going to be back down at -1. So what two numbers am I between now? So if I was down here at -1. Oh wait, I'm drawing it in the wrong spot, all right. -1, comma, -1, -1, so here. So what two x values am I between now? -1 and 1, right? So what if we made it, tried like 0? What do I get when I plug in 0? 1. So when I plugged in 0, I got 1 above. So now I'm between 0 and 1. Does this make sense? And then what would be the next thing I would try?
0 and -1 or 0 and 1?
I think 0, these are the x values here. So I'm between 0 and 1. I know, my sketch isn't the best. So now I would try like 1/2, right? So let's go ahead and use a calculator to try 1/2. So if I have f of 0, or f of 1, I mean, or 1/2. So I'm going to have 1/2 cubed minus 1/2 squared plus 1. So that's at 0.875, which is above the axis again. So now what two numbers am I between for my x values? 1/2 and 1. Does that make sense? So our interval, 1/2 to 1. Okay, so we're just kind of finding numbers that we're squeezing between. Now what is your calculator doing? Like if you're using a calculator to find a 0, it's doing the same thing. You're doing that on your calculator. Do you guys know when you do left bound, right bound? That's what you're doing. And your calculator yells at you when you don't have them both like one above the axis and one below the axis. Has that ever happened to you where it's like, wait, you didn't do that right? That's what it's doing. So it's squeezing it between two numbers.
Why don't you put bracket 0.8?
Oh yeah, that should have been 0.875, thank you. No, it's 1/2.
No,
It's 1/2.
the one side of it. Like, why is that 1 and not 0.875?
Because you're on this interval. Whenever you use the word interval, those are x values. So the 0.875 that you found, whoa, I misspelled values. The 0.875 was a y value. So I'm never going to say between this x value and this x value and use that 0.875 number. So we're saying between 1/2 and 1 is where it's crossing. It's crossing somewhere between there. So we found one that was above the axis and one that was below the axis, like a left bound, right bound situation. All right, and you could keep like making it smaller and smaller, or you could use your calculator if you wanted to actually find the decimal approximation. All right, so it says show that there's a root of the equation on the interval -1, or -2 to -1. So now I'm not saying find an interval of a certain size or anything. I'm just saying show that there is one. Okay, so if I'm using this intermediate value theorem, I want to find like f of -2 and f of -1. Did I ever talk about f in this equation though? No. So one thing that I teach my calculus students is that you have to do a let statement. You have to say like let f of x equal 3x to the 4th minus 5x squared plus x minus 2 before you start saying things like f of -2 and f of -1, because your grader would be like, wait, what's f? Right? They're tricky. They want to make sure that you're writing it correctly using correct notation. So this is where I would plug it in for just my y equals, my y1. So I can do both at once. So I'm going to do 3x to the 4th minus 5x squared plus x minus 2 for y1. And if I want to get both of these values, I could just easily go into my table, and I could plug in -2 and also plug in -1. So when I plug in -2, I get 24, and when I plug in -1, I get -5. So again, think about what this is saying. So it's saying on my graph, at -2, I'm way up at a height of 24. I know this clearly isn't drawn to scale. And at -1, I'm at -5. So if I have a polynomial, so I have this kind of continuous curve connecting them, I have to cross somewhere between -2 and -1. That's what we're saying. Okay? So I'm going to say f is, you could say a polynomial, or I usually say f is continuous. Like I'm not jumping from a y value to another y value. And the first one was positive and the second one was negative. So f is continuous. So there must be a root or 0 or whatever you want to say on -2 to -1 by the intermediate value theorem. Do you guys want to write out intermediate value theorem? Probably not. We use IVT. All right, does that make sense how we do that? Okay, so basically whenever you see a problem that says use the intermediate value theorem, all you're going to do is you're going to find like the y values on the endpoints. So if you have an interval like between -3 and 5, you'd find f of -3, f of 5, show that one's positive, one's negative, so there has to be an x-intercept between. But it really works for anything. Like if I wanted to show that it went through y equals 2, I would just show that one of them's above 2 and one of them's below 2. And then I could use the intermediate value theorem. Okay? All right, so let's stop there.